Hello everyone, we now present our work entitled 3D-NOD, 3D New Organ Detection in Plant Growth by a Spatiotemporal Point Cloud Deep Segmentation Framework. The presentation consists of 5 following parts and will cost you about 10 minutes. With the rapid development of artificial intelligence, the deep networks are now powerful enough to handle different 3D plant phenotyping tasks. For example, deep networks can be used to classify the species of a plant point cloud. Deep networks can be used to carry out organ semantic segmentation on point clouds. The networks can also be used to segment each single leaf instances from the canopy, and even detect and segment new organs. However, the application of deep learning on plant phenotyping is not that simple. The balancing of the different classes in training data can greatly influence the learning process. If the dataset is balanced and well prepared, then the network is almost guaranteed to output good results. But if the dataset is imbalanced, the training network will be very likely to be insensitive to the small classes, and this phenomenon is quite network irrelevant. Unfortunately, the class of new organs is too small compared to the mature organs. Therefore, using a conventional deep network to detect or segment new organs quickly falls into the imbalanced training problem, and usually obtains insensitive detection results for new organs. The conventional frameworks for new organ detection train and test on single point clouds, which easily results in a low detection sensitivity on new organs. But we think growth is a concept closely related to time. Thus, this research argues that the detection of growth events should not only focus on changes in space, but also on the temporal correlation in plant shape. We propose a spatial-temporal framework, 3D-NOD, that inferences on both time series plant point clouds and a single point cloud. This is the detailed framework of our 3D-NOD. It is composed of the training pipeline and the inferencing pipeline. In the training pipeline, the original time series plant point clouds are labeled for training by the backward and forward labeling technique. The labeled point clouds are then downsampled and fed into the registration and mix-up module to generate mixed point clouds of 2 adjacent stages. Then the training data is augmented 10 times by the Humanoid Data Augmentation method, and the modified DGCNN network backbone is used to train these data. In the inferencing or testing pipeline, the time series plant point clouds for testing are first downsampled and fed into the RMU module to generate the spatial temporally merged point clouds. Then after network inferencing, each merged point cloud is first split in time, and then the results are refined to further increase the detection sensitivity on new organs. In the next few slides, we are going to explain what we did in each steps. Traditionally, new organs are labeled on each time point, which ignores the temporal correlation in growth. We noticed that an experienced human worker usually compares a point cloud with adjacent growth stages to better identify new organs in growth. This enlightened us to propose BFL, a labeling method that tries to identify more new organs and buds in the training data by comparing the plant back and forth with itself in the timeline. The manual labeled point clouds are then downsampled by the FPS algorithm to fix the point number at 2048. In the next step, every 2 adjacent point clouds in time are spatially aligned by using the ICP algorithm to generate a mixed point cloud. Then the mixed point clouds of two adjacent stages are fed into the Humanoid Data Augmentation, HDA for short, for training data augmentation. We have noticed that experienced humans usually subconsciously use three operations to better identify new organs when comparing the two adjacent times of a plant. Operation 1 is the rotation of the merged point cloud as a whole. Operation 2 is the rotation on only one point cloud in the mixture. Operation 3 is the small translation on only one point cloud in the mixture. We drew inspiration from the operations and designed HDA. HDA uses three cascading steps to imitate the three human operations. Operation 1 rotates the mixture with a step angle of 36 degrees to generate 10 different views. Operation 2 rotates one of the point cloud in all 10 views with a random rotation angle between 0 degree to 5 degrees. Operation 3 then conducts random translation on one point cloud in all 10 views with a random distance between 0 to 0.15. After HDA, we can augment each merged point cloud 10 times. We used a modified DGCNN backbone to segment new organs and old organs. The network accepts a merged point cloud with timestamps as inputs, and each input has 4 dimensions. The first 3 dimensions are the XYZ coordinates, and the last dimension is the timestamp to indicate whether the point is from the previous time or the current time. The network output has a size of 4096 by 2, which shows the new organ and old organ segmentation scores. The processing of the testing pipeline is a little bit different from the training pipeline. After the merged testing point cloud after RMU is fed into the network, the output is a segmented mixture that should be split into 2 separate times. As the example shown in this slide, there will be 2 ambiguous T-2 stage results. Therefore, we designed a refinement step that used an OR gate to improve the detection sensitivity on new organs from both results. We prepared a spatial-temporal multi-species dataset containing 37 growth sequences. The dataset also provides carefully annotated new organ and old organ labels for each single point cloud as ground truth. The training set contains 25 sequences, and the testing set contains 12 sequences. In the quantitative experiments, we compared our 3D-NOD with several other networks with the conventional way of organ detection on the dataset. 4 metrics, including precision, recall, F1, and IOU, are used to measure the performances. All training and testing data was only divided into 2 classes, old organ and a new organ, for all compared methods, which means we did not distinguish species in this comparison. Our 3D-NOD has the best result across all networks. In the qualitative experiments, we contrasted 3D-NOD with ground truth in several testing sequences. The results are similar to human annotated ground truth in most cases, showing a high sensitivity in detecting tiny buds of different crop species. We compared our full 3D-NOD framework with 7 ablated versions, each of which was formed by removing an existing step or some parts of a step from the original 3D-NOD framework. Removal of any existing part will cause a decline in detection performance, and this proves all proposed modules are effective. The standard 3D-NOD trains offline on past spatial-temporal sequences. When testing and inferencing, the framework has to wait until at least 2 stages of a plant are collected. Therefore, The standard spatial temporal testing is not purely real-time. But if we make a little modification on the input of DGCNN in the testing stage, then 3D-NOD can do online testing from any time point. This helps to realize real-time phenotyping. We compared the ground truth, the standard spatial temporal 3D-NOD testing, and the 3D-NOD testing on a single point cloud in qualitative experiments. The testing on a single point cloud traced a slight performance loss for real-time ability. Finally, we show parts of the visualized supplementary materials of the paper. The full supplementary materials are attached with the paper submission. This slide is a partial visualization of original tobacco data. This slide is a partial visualization of original tomato data. This slide is a partial visualization of original sorghum data. This slide is a partial visualization of tobacco training data after RMU. This slide is a partial visualization of tomato training data after RMU. The slide is a partial visualization of sorghum training data. This slide is a partial visualization of tobacco testing results. This slide is a partial visualization of tomato testing results. This slide is a partial visualization of sorghum testing results. Thank you for listening.